What's up? All right, we're going to learn about the anatomy of a wave. So in order to complete this page, you're not just going to draw all of this on your own. You need to go back to the extras bin and grab one of the half sheets that looks just like the one here in the video notes, and it is called Anatomy of a Wave. Go ahead and tape that into your science notebook, and let's take a look here at our wave. Now, waves are really, really important, and we actually interact with them all the time. You listening to me right now is a function of the fact that the wave was able to be taken through the air, through the microphone, and put into this computer. The computer is now sending you this information through waves. So you can see we've got in our box here a picture of a wave, and these waves are important because of the reasons I just described, and so we need to be able to identify the parts of the wave that make them important and make them different. So to begin with, you can see this little dashed line here. This dashed line is what we'll call our line of origin. Now, the line of origin is important because in order for us to measure how tall the wave is, we need to be able to know where the line of origin was so that we can measure the height of the wave, which we call our amplitude. Now, I like to think about amplitude in terms of like being super gnar. If you think about like the X Games and the skateboarder goes up the half pipe and gets way out of the half pipe, or the skier, and they do some sick trick. They're like, whoa, check out that amplitude. He's getting way up there. And that's like getting higher up off of that half pipe. So therefore, that term in extreme sports, amplitude, is directly related to this idea. It's like the height of a wave. We could also measure the amplitude by going from the line of origin down to the bottom of this wave part here. Now, that very, very top of the wave, that part is called our crest. So I'm going to put a little dot here and label this as the crest of the wave. And this part down here, the parts that are at the bottom of the wave, these are our troughs. So we have our crest and our trough. And the crests and troughs repeat each other, and that's what makes a wave. So there's not just the one crest, there's also the second crest over here as well, but I'm not going to label that one. Now, in order to know the length of a wave, we call that our wavelength. We measure it from one crest to one crest, so we get one complete cycle of the wave, and we call this our wavelength. Now, sometimes in physics, wavelength is a long word to write, so physicists like to be lazy and write it with this type of Greek, this Greek letter here that I think is the mu or something along those lines. But you can see it's that diagonal line with a little curved line on it. It looks like a slide kind of, and that is wavelength. That symbol will indicate wavelength. All right, so you could also measure wavelength from the trough to the trough if you'd like. But for this example, I'm just measuring it from the crest to the crest. So if you measure it from the trough to the trough or the crest to the crest, the wavelength should be the exact same if you're measuring a wave. Okay, well, the frequency of a wave is just simply the number of waves it can't just be the number of waves. We have to quantify how long we're going to measure for. So it's the number of waves that occur over a specific period of time. It's usually for 1 second. You count how many waves occur in that 1 second, and that's usually measured with hertz, which is Hz is the unit for frequency most times. All right, well, there's two different types of waves, and we'll go more in depth into these, but a transverse wave is kind of what I've been drawing here. And when we draw waves, we're going to pretty much draw them as transverse waves to signify their amplitude, their wavelength, and we can turn these waves into transverse waves, but not all of them travel as transverse waves. Some of them travel as longitudinal waves. So longitudinal waves, when you draw these, I like to draw them like this. You can imagine like a slinky that's sitting on a table. If you were to push one side of it, a bunch of the slinky pieces would all group together. So I'm going to just draw a bunch of little half circles right here to show that all groups together. It spreads out as it transfers the energy, then that energy gets collected in this point, and then it transfers it to the next section. So you can see there's a compressed and a stretched portion of that wave, and that's what makes it a longitudinal wave. And finally, the reason that waves are so important in our everyday life is because they transport energy. So as we've discussed, energy cannot be created or destroyed. So, if you have potential energy that you drop through motion energy with a book that hits the table, that sound energy is a form of energy, and that would be an example of how motion energy gets turned into wave energy. So let's talk about that, sound waves. Let's dig into that in our next video lecture. I'll see you there. Peace.